Again.
Okay. Oh yeah, it started. Someone has started Ajit Kumar. Yeah.
Okay.
Yes. Yeah. So today in this notebook, what we'll be covering is the details and each component of the transformer model. And as you have any doubts as it arises, you can ask in between because I'll not be able to see the chat screen when I'm presenting this. Yeah. So for beginning the background part, we normally start with the sequence to sequence model. So what we mean by sequence is any given text is considered a sequence and the output of the model is also expected to be a sequence. How this differs from other type of models is you can have like classification models or any model which takes a text as in or sequence of text as input and gives a particular label or token as output. For example, in classification, you can give a sentence as input to be classified as, for example, in sentiment as positive or negative. So your output will be a single token, positive or negative, or in fact, it will be just a number 0 or 1. So contrast to that, these models we are focusing on a sequence to sequence where the output also is in text. And that text can be either a summary of your input, or it can be a translation of your input, or it can be a continuation of your input, depending on, or it can be an answer to the question which is your input. So depending on what task we are focusing on, this input sequence and output sequence will vary. So that is the basics of sequence to sequence models. So looking at this, these images show the different examples of the sequence to sequence. So we have like summarization and even code translation and also image capturing. So this is to show that your input sequence is not restricted to text. It can also be an image, where in your image, if you take the RGB values, those values, if you take that matrix, it will also form like a sequence of input numbers as input. And the initial methods which were used for the sequence was this something called RNN, that's recurrent neural networks. So in this part, I'll not focus more on this RNN. Like you can go through this text later and as doubts as you can ask. But the main focus will be on the transformer part of the model. So these are just the information for the RNN and how it works and all that, and why we no longer use RNN. So one major drawback of RNN is that since it works in the sequential manner, from where you start from the input token and then you need to take the next token in a serial manner, transformers can act in parallel. That is, it is more computationally efficient and can handle batches of input much more faster and better compared to this RNN model. So that is a main advantage. And because it's improving the computation efficiency, you can start scaling up the models and feeding more larger data as input and getting more better performance. And along with the increase in computational resource availability and the cost of that, that's how we are able to see the advancement in the large language models now and the past 1-2 years compared to the few years back. So before 2018, you don't see much about this large language models, but recently in the past 1.5 year, 2 years, you can see multiple language models which are even larger than previous models. So that is the motivation for the transformer. So that architecture has made it parallelized computing much more efficient. So looking at the transformer model, so this is just like this is not a transformer, but this transformer is required to run our transformer, what we are talking about. So you can think of it in the beginning as a black box. So what in this notebook will be going, the approach we will take is like a top-down approach where we look at the whole module level and then go deeper into each layer. So it's like a top to bottom view. So looking at from that angle, first we can assume the transformer to be a black box where you give a sequence as input and get a sequence as output. Depending on your task, that input and output sequence will change. So if you zoom into this block, you can see it consists of two further blocks. So the first block is called encoders and the second block is called decoders. Now from here, if you see from this aspect alone, this image alone, you can start seeing a divergence of models where you would have heard of something called decoder only models. So the GPT family of models is all decoder only models where it consists only of this decoder block and doesn't have this encoder block. And this BERT family of models has this encoder block. So later we'll see the advantage of having both and having only the decoder. So for now, the transformer architecture as proposed in the paper in 2017 is having both encoder and decoder. Now, if you further zoom into this encoder and decoder blocks, we can see that whole block consists of multiple sub blocks, each consisting of a module called encoder. So the name is same, but yeah, the group of encoders is called this whole encoder block. So now our task is to further zoom into this encoder and further zoom into this decoder. And that's where this image comes, which is the most popular image of transformer. So anywhere you see transformer, this is a standard image in the paper and always used for explaining transformer architecture. So if you look at this, you'll start with your input text, which you'll pass to an embedding layer. So since your text is of characters and models always take numerical input, you need to convert your characters to numerical format, which is done to this embedding layer. And when you do that, you also pass a positional encoding. So later you will see when discussing the attention part that sometimes the just direct attention does not capture the positional information of the text because it's a way of averaging or weighted averaging over the tokens. So in that aspect, because you average or aggregate, you don't capture the positional information. So, but positional information is necessary for us to understand how the text is. That's why we additionally add a positional encoding, which is also passed as input to the model. So having these, I mean, it's added to the input embedding. So your final embedding will be consisting of your text embedding along with the positional embedding. And this is passes input to your encoder block, which if you see this NX, that means that you can have multiple encoder blocks similar to the image above. So if you look at into deeply, you'll have a multi-head attention layer followed by an addition and normalization layer. So what we mean by multi-head attention, first we look at single head attention, then we look at multi-head attention. So just you, for now, you can imagine it as in a block, which does some kind of weighted averaging over your tokens to calculate how much information or how much attention or importance needs to be given to the tokens are there. So for example, you're looking at a given bird and it has the surrounding words. How much importance should I give to the surrounding words? That calculation is done by this block, orange block called multi-head attention. And then you do this addition and normalization. So addition and normalization is always a standard step, even in deep neural networks and all machine learning and deep learning, so that your variance and because all these weights what we initialize for these layers, they are randomly like initially they'll be initialized with maybe zero mean and variance. But when as you progress to the training, these values will keep on changing. So to ensure that we're always within the bounds, we always do this addition and normalization. So once we do that, we pass it through a linear layer, which is also known as the feed forward layer. And linear is nothing but like you can take, imagine as a neural network layer where you'll have an input dimension and that will be calculated with weights and biases, and then output will be output dimension. So whatever dimension you mention, that matrix calculation can be, weight matrix can be manipulated accordingly to give you a desired output shape. And that is again added and normalized. So this, if you see over here, there is another arrow mark going directly from the, after you pass the input, instead of passing the multi-head attention, there is the arrow mark directly going to this additional normalization layer. And the same thing can be seen even in the linear layer or feed forward layer. That is called as a skip connection or residual connection. And the importance of that also we'll see later when we go in detail to that part. But for now, you can just be aware that we have an attention layer, we have this linear layer, and we also have the skip connections to add and normalize. So that's where the addition part comes. What we are adding is nothing but the output of the attention head in this instance, along with the input directly passed without passing through this attention layer. And finally, we normalize the whole thing. Similarly, for the second block, we add the input, the output of this previous block along with the output of the linear layer. We add that and normalize it to get the final output. This is regarding the encoder. When you look at the decoder, it has a similar architecture to the encoder with one key difference, where one difference is you have this additional masked multi-head attention. So if you see the other two blocks, this multi-head attention and feed forward, both are identical to the encoder. Only difference there is the input changes. So here, if you see the input, we have three arrows. So the significance of the three arrows also will be going in when you discuss attention. But for now, you can think of it as the input. It will be split into three parts. That is considered as a key, query, and value. So that when we take as input, your key, query, and value all come from the same input. So that's why you have a single arrow. Whereas if you look at the decoder part, your query alone is coming from your like the output of this, but your key and value is coming from the encoder part. So its significance also we'll discuss once when I go to that multi-head below part. For now, you can imagine that the multi-head attention in the decoder part has your input dependent on the input to the decoder as well as output of the encoder. Whereas your multi-head attention in your encoder part has only input as whatever input we pass in. So that is one difference. And that's apart from that, the other main difference is a masked multi-head attention, where we'll have the notion of masking out few of the tokens which come in future. For example, you have a text or a sequence of length 10 tokens, and currently suppose you're focusing on the fifth token. Then by intuition, when you are able to see only the 5 tokens, you have no awareness of what the next token can be currently, unless the next token is time step comes. So for the current time step, you can only information you have is your past, which is the previous 5 tokens, including yourself, the current token. So that's why the future tokens we mask out to show that act it as we can only see the past, we cannot see the future. So this also will go in detail in full. But for now, it's just an overview. And again, it's
Just
input also. Yeah.
Yeah, one question. So in the self-attention layer,
Mm,
when we do, we find out the query key and value vectors, right? So I
yes.
just want to know that why the three vectors are being there. No, is there any logic behind that, or what information does those vectors contain?
Yeah, I'll discuss that in detail when I go to that attention part. Like, yeah, it'll be covered. Yeah, like for now, if you want just an intuition, you can think of as query can be like the main idea of attention is to find out what your tokens around you are trying to, what information they contain, and is that information relevant to you or not. So that's how we can decide whether I have to give importance or some value or weight to that token. So by having something called query, what query can signify is I'm looking for something, like what I'm looking for. So that can be designated as query. And the key can be what I have. So if you do the dot product of what I'm looking for and what I have, its dot product can give a number, and higher the number, you can interpret it as having a higher similarity. So dot product is like cosine similarity, similar concept. So where if your two vectors dot product is high, that means both are very similar. So in this context, if you multiply that query and key values of different tokens together, if for 2 tokens the query and key value product is very high, you can interpret as those 2 tokens might be more relevant to each other. So that can be the intuition for the key and the query. And the value part is once you calculate this weights, finally you need to propagate it to the input x, right? So instead of taking x directly, we also take x as values. So that it's more I mean that is also a learnable parameter. So what we finally calculate is your attention score, which is the key and query, multiplied with the value which is obtained from x only.
I didn't
So
got
that
the value. We didn't got the value part. What does it signify?
it signifies what information is actually conveyed to the final model. So your input x is the raw information. When you pass it, when you calculate the key and the query, that is like what I'm looking for and what I have. And then when you calculate the value, it is like what information is actually propagated through the learning model. So that is also, so yeah, the reason
My
for that is instead of directly keeping x, y, you're keeping value. Is that the question?
No, my question is basically the query key and value vectors are nothing but the the input x multiplied by that w
Yes. Yeah.
of the key and the query and the value vectors, right? And they are
Yes.
those weights are learned by back propagation.
Yes.
So, and we are not essentially, the training wise, we are not giving any particular kind of special treatment to any of those vectors, right? So how do we say that query is different from key or keys are different from value? And the second question is that basically when we are doing it, that is the weighted, finding out the weighted sum of the value, that is q dot qi dot ki by into the value
Mm.
part, right?
Mm.
So what is the basic reason for that? To why we are basically, because if the q and k are not different as per the logic that I told you, then what is why we are doing it in a special order? So
Okay.
that was my wish.
Yeah. So I'll address your question. So starting with query and key
So
are
my
actually different.
once again, my
Yeah.
request to everyone will be to consider this to be a tutorial session where we explain the working step by step, and in case you have to implement this thing, so how do you take care of all these in details? So uh, yeah, I think keep that in mind while going through this tutorial. It will help everyone.
Okay. Yeah, regarding that previous question, actually key and query will not be identical. Although the input is same, your final values will be different because we're using two different linear layers for initializing and getting the final values. So your content numbers will not be same. So since it's not same, when you do the back propagation, the way it's updated will be different. So everything won't be identical. So, and the second question was the significance of having this query and this thing. Yeah, I'll go through that in detail when the attention part comes. For now, like we'll just go through the stepwise, like starting from the encoder part. That part I will cover in the next section of attention. Yes. So
Okay.
coming to this thing, we have this addition. This part is similar to the encoder block, and finally you have the linear and softmax layer, which will give the output. So if you see this textual content, again, you can go through on your own time. Like I will just go through the code part, which is crucial over here. So this is, we are importing some libraries, which will be useful for the coding part. Yeah. And then this is mostly the torch library and different parts, like for example, the data loader for any data you want to input, and this log softmax, the softmax function and all that. And torch.nn is again for the linear layers to load those. So we'll be starting with this class called encoder decoder, where if you see, you'll be having the encoder block and the decoder block. This is similar to the image which we saw over here, having this encoder block and decoder. So this image, this is what we're trying to replicate in code over here. So looking at keeping that image in mind, you can see that we have declared this encoder and decoder. We also have the source embedding and target embedding. So because we pass in the input two times over here, like input and output, that is. So that's why we need a source embedding and also a target embedding. And then we have this generator. So the generator will will define it over here below. That's nothing but this linear layer and the softmax part. So that part will cover next, but before that's just initialized over here. This is the initialization. And when you do the forward for this encoder decoder block, what we do is we take your input, which is your source, along with the attention mask, which we call a source mask, and pass it to the encode module. And once we pass output of this encode module, needs to be considered to as input for the decoder module, right? So we have that along with the source mask, because that is similar, masking will be same propagation. And we also have this target, which is actually the output, which is taken as input to the decoder part, and the target mask. So this will be passed as input to the decoder module. And this whole thing will be one forward pass of the encoder decoder block. That's the whole transfer module. And to call encode separately, we call the encoder module, which we'll define below. And to call decode separately, we'll call the decoder module. So that's what action will be taken. So for encoder, the input will be your source embedded text and your mask, input mask. Whereas for your target will be the target embedding of the output, expected output, along with the masking capabilities. I mean, the masking that whatever for the relevant input, you need the associated mask. So this is for the just broad overview of that image where two blocks of encoder and decoder. We'll be
Yeah,
defining
one
each of this
question.
function. Yeah.
Why are you using source mask here? Masking is done at decoder level, right?
No, that mask that is the history. I mean, the future masking. This mask I'm talking about padding mask. So in
Okay.
case your input text you need padded, right? So that zeros and ones. That mask attention that is different. This is different. This is for the because when you batch the input, you need to for the padding mask. This is.
Okay, thanks.
Also, what is the memory part here in the decoder?
Yeah, I will discuss that when you go to the decode function. So that is also taken as input over here. But when I discuss the decode function in detail below, it will be more clear. So that's why I'm telling, like, this is a top-down approach. So some things might not be clear right away, but as we go deeper, it will be clear. So this is to taken from overview broad as perspective to a smaller, like inner perspective. So that's why everything might not be clear at once, but it will become clear as we go ahead. So here we defined one function called as generator. So what that generator actually that class stands for is it defines a linear layer, which we are calling as a projection layer. And when you call the forward of this generator, what it actually does is it passes your input text to this projection or linear layer, and it calculates this log softmax. So if you go back and look at this part over here, your linear layer and your log softmax, this final two blocks. So that's what is called as this generator function over here. So your this image of two blocks of encoder and decoder, along with this final output of decoder you need to pass to linearly and softmax, that part is taken care of with these two classes, encoder class and this generator class. Now we'll be going deeper into this encoder and decoder function. So if you see at the encoder, again, if you see, it will consist of this attention block and the feed forward block. So if you zoom into this even further, you'll see that attention is actually called self-attention in this aspect context. And you, after you calculate the attention, you do this layer normalization of this X and Z. So that will be the your skip connection along with your output of self-attention. And then you normalize that after you add it. That's why layer norm is normalizing and this addition part is covered here. And output of this is taken as feed forward layer, and again its skip connection is again added and normalized. So this self attention, when you zoom in, this is what you see. So the yellow one is just the direct input without attention, and the Z1 is after you calculate the attention and you add a normalized. So this part we'll try to start implementing. Before that, since you would have noticed this encoder number one, we'll have multiple encoder blocks. So to make it easier to create copies, we have this copy clones function where you pass in the module. So the module can be that encoder block or decoder block or whichever layer we want to multiple times we want to copy. And we just have this deep copy function. So this is just to create copy of multiple modules or layers. Coming to the encoder class, initially we'll initialize the layers. And since encoder can have, it can have multiple encoding blocks, right? So you suppose that n will define over here. So how many layers, suppose we want 12 layers or 6 layers, we can give that number. That will create that many clones, and this layer will, if you pass the encoding, that encode layer, it will get encoded, like it will be copied that many times. And the layer norm layer, so because every time we do this encoding, you also need to layer norm and let's normalize. That's why we have defined that also. And layer norm again will define below when we actually go through that part of the code. So for forward, for every layer which we have copied over here, we need to pass your input along with its associated mask, padding mask, and get the output and do the normalization of that. So that's just what this encode does in superficially. That is just this part. But actually we need to go deeper into how exactly this, what layer we pass into this clones. So before that, we have this sublayer connection. So this sublayer connection is nothing but the residual connection, which we call a skip connection over here. So we also need to define that as well, right? So for that, we have again this normalization and dropout. Again, dropout is like a regularization parameter, which if you include in your any modeling, it seems to give better results than not including. And it, so that's why like dropout is nothing but it'll just ignore that weights as you train. Like some weights will be masked, like brought down to 0. So in that forward function, whatever input we have, we'll get that addition with the sublayer norm. So that sublayer is the one which you get through this attention or through the clone or whatever layer we are calling. So for here it will be attention layer, and here it will be this feed forward layer. So this is called sublayer, and this sublayer output, that is Z1, will be added with the X directly. So that's why we are adding this X directly over here. So that's the main part of this residual connection, which we are calling a sublayer connection here. Now that these two parts are taken care of, we can further define this encoder layer. So if you see, what we defined previously was this clones of layer. So what exactly that layer part we didn't still clarify. So that's what we'll be doing over here. So that one layer of the encoder layer will consist of the attention, which is self-attention. It will consist of the feed forward layer. It will also have this residual connection. That's why we are having this sublayer connections. And the size, whatever size we mentioned, that dimension size will be followed. And when you do the forward pass of this encoder layer, your initial X will be calculated for self-attention. And once you do that, you have to go through the skip connection with sublayer and then repeat the same thing with the feed forward layer. So now you will come to know like how the normalization and addition part is taken care by the sublayer connection, right? So the first line over here will take care of calculating the attention and adding it to the previous in the original input and normalizing it. The second line will take care of the feed forward layer on its output and adding it to the previous input to that layer and normalizing it. So sublayer will take care of normalization and addition. other two parts will define again below. So what exactly is self attention and feed forward will be defining below. So now we'll come to the attention part. So if you look at the reason for attention, which is very intuitive, is that which token should I pay attention to? So given any list of tokens, if you look at this, actually this colors will be defined when you will be more clear when I discuss the multi-head attention. For now, imagine there's a single head and you're focusing your input X, the X is it underscore. So for it underscore, which of the words around the sentence is relevant to it? And that weightage matters. So if you see the darker color here indicates a higher number. So that means your the animal is more relevant to it rather than this because or cross. So that also logically makes sense because if you look at the sentence, what it is actually referring to is the animal. That's why the animal's weights are higher. So that's the intuition behind attention and the reason why it has been more helpful and useful to calculate that. So if you start looking at the details, so this is what the X and key query value part will come. So here I would just like to show you starting from a more simpler approach of why it is useful or valuable to calculate attention rather than just taking an average or something. So this part is actually referenced from this video by Andrej Karpathy. He is a very famous computer scientist and he has done many videos on NLP and even AI also and GPT and everything. So based on that video, this part I would like to explain so that it's more clear. And later you can refer to that video as well. So if you'll start, just for example, normally your input will consist of a batch dimension because we are doing multiple batch processing. So any batch dimension, then it will be having a token length or sequence length. So your input sentence length, whatever length we define, and there'll be an embedding dimension. So that, for example, over here, I have taken the batch dimension to be 5, the token length or the sequence length to be 10. You can keep it any length depending on whatever input sequence you're giving. And your embedding dimension, that's depending on the embedder layer, what we define over there. Over here, just I have taken for now as 16. And now when we want to, if you imagine how a input would be, we can just for now take a random value. So for X, you can imagine that currently X is a matrix of size, batch size into sequence length into the embedding size. So 5, 10, and 16 in this case. And just to look at some instance, so looking at batch 0 and looking at the first, all the, this vector represents the first token and each vector following represents each one token. So one token is represented by the 16 dimension vector over here. So there are 10 tokens indicating the one sequence. So that's what this X contains, like how probably it will look like when you embed your text and go ahead. So now I'll just go through the intuition behind that aggregation and attention part. The thing is starting with your simple aggregation. So what if we just take the average of these tokens that passes information to your model? Why do we need this 3 separate layers and all that things? So to try that, we can take, for example, your A, for now just a temporary matrix, which is ones consisting of ones of size t cross t, where t is the sequence length or token length. And then if you look at A, it will just be, suppose t over here is 10, it will be a 10 by 10 matrix with all ones. And then if you take the sum along the second dimension, that's the last dimension, and maintain the shape, you will get this 1 cross 10 vector where you'll have the sum of all the elements. So since our t is defined to be as 10, that is the token sequence length, that's why we have 10 over here. And when we take this average, or you calculate the average by taking A and dividing by the sum of along each row, what we get is the 0.1 across everything. So this is what a simple averaging will look like. And if you use this to multiply with x, so this is what we do, A dot x, this is dot product, we'll get something of the shape 5, 10, 16, because your A shape is B cross T cross T. So that T and T is the 10 and 10. And your shape of the x's input is batch and token and embedding dimension. So when you take the dot product, your final shape will be B across T cross E. So that is the 10 cross the 16 dimensions. So that's what we have over here. So if you look at these values, you can see whatever our x we initially randomly initialized over here, we can see how it has been changed over here. And we also can compare that with the final value what we get by looking after calculating this averaging. So this is the raw x value, and this is the x after we do the averaging multiplication, the dot product with that average part. So if you look at these values, the final vector, I mean, what we have is actually the average of all the previous things. So if you try to just cross check that, what we have as the last one is same as the mean of x along that dimension. That's the second dimension. That's the last one. So this means what we have essentially done is for every token, all the around surrounding tokens are given equal weightage. And now this can be very intuitive and very naive approach, but what we desire is something which is data dependent. The way we want to calculate these weights, instead of having it uniform across all the tokens, we wanted to have some changes which indicate or which reference back to how important that token is to the other one. So for example, it and the animal, we want the animal to have a higher weight because it is referring to that. So to do that, what we find out is that we can introduce this linear layer of two types. One linear layer to calculate what is the expected, like what we are looking for, and another linear layer to show what we have. So this is like an initial conversation between the tokens where you try to figure out whether this token is relevant to me in some aspect, like just in not the exact final value, but in some aspect, is this token relevant to me or not? And if it's relevant, to what number or what weight. So for that, over here as an example, we can introduce two linear layers, and we can see that to calculate the key, we just pass our input x to the linear layer one, we'll get the key. So here you see, since I'm defining two separate linear layers, the weights will be different. So your output of key and query will actually be different. And if I try running this and showing you, I'll just reconnect it and run so that it is more clear. Yeah. So I'll just run this part. So here I'll print out x first. So if you look at x, which will come over here, you can see that it has some long, it's a only the zeroth, the first batch I'll print instead of printing all the batches. So it's easier to see. So if you see, this is the actual x value, what we have initialized. Now, if you look at the key part, after passing through the linear layer, first, if you look at the shape of the key dimension, what we have is 5, 10, 1, and our input dimension is 5, 10, 16. So reason 16 became 1 is because we have called this head dimension as 1. When you call multi-head, your head can be, instead of 1, it will have 8 or 16 or 12 or whatever number. So that's where the multi-head part comes from. So currently, for understanding purpose, I kept it as 1. So it's a single head attention. And the advantage of multi-head also I'll show below. But for now, imagine the single head. And looking at the key part, how its values look like, you can see it will have this dimension because your last dimension is only 1, and your initial batch dimension have taken only as 1 batch, so 0, and your remaining length will be your t dimension. So that's why you have only this t dimension, that's 10, 1, 2, 3, yeah, and 10 values of your key. And if you look at this same thing for value, you can see that both are not in fact identical. So although your input to both are identical, your actual values what we have are different. So that's where the first difference will come from. Oh, sorry, I have to search the query, right? Okay, like it's taking time to run, but yeah, when it comes, I'll show it back. That it'll be identical, it'll be different from the values. So calculating the attention score for that, what we do is we multiply this query with the key. And since its shape is same, we need to do the transpose. So we have this initial shape as b cross T cross H, but what expected shape will be after doing query and key will be B cross T cross T. So when you calculate the attention score for that, we can see its dimension will also be B cross T cross T, and its values. Okay, this part is not showing, but its value over here will be something like this. So if you look at this, it seems to have this negative numbers, right? Normally, when we calculate attention scores, we don't want negative because it doesn't signify a value importance. What we would desire is a uniform distribution, like a softmax kind of weighted probability. So for that reason, we actually pass this through the softmax layer. So that's why if you look back at that attention function definition over here, if you see after you calculate your query and key, you divide by this underscore dk. Dk refers to the head, the dimension of the head. Since we are keeping it as 1, it may not be considered for now. But later when you do multi-head attention, it will be relevant. And that is passed to the softmax so that we exponentiate and normalize. So that your weights, what we calculate for the attention, are not in negative numbers. And that whole thing you multiply with value. Value is again part from the input x only, but it's a different linear layer. So that will be this linear layer 3. So that will be your value part. So value will be the actual information conveyed. So, and this will also help you maintain the dimension what we want, and also help in keeping the learnability aspect preserved. So if you just multiply x directly, like in this case, instead of value, our expected output shape will be this B cross T cross E, where the embedding shape will still be maintained. But if you don't want that embedding, because embedding dimension can be even 50,000 K or something, depending on what tokenizer and what vocabulary we are using. So to avoid that, to maintain this whatever shape we mentioned with the heads, we can use this value layer. So that'll in one convey the information of X, and 2 also help in maintaining shape, and 3 also help in containing the learnability. So because value part is also learned, the information which the token is sharing to the attention score, like what is being represented, can also be modified to learn some concept. So it doesn't need to be static. So if you look at this, your X static input has been converted into a dynamic or learnable key value and query. So that's what we get. And another advantage of having this value separate instead of having X directly is that when we discuss cross attention, where your key and your value will be coming from a single source, but your query will be coming from a different source. That's where the decoder and encoder cross communication comes. In that case, when your inputs are different, it will be useful to have this value function also. Like it need not be same as your it doesn't make sense to have it same because you're communicating across 2 different, so you want everything to be learnable. So that is the intuition and reason for having this key query and value. And just to go over it once in through images, if you look at this image, your embedding X, which you use to calculate this key query and value, this is in case of self attention. In cross attention, the only key difference is that your queries will be coming from a different input, whereas your keys and values will come from a different input. So that's the difference. And with that weights, you'll be having this calculation of dot product to give some numbers. And that will be passed to this division. The division head is for in case we have multi-head. So in this example, they're taking it of head of 68. Like, so when you divide by 8 of this 112, you'll get 14. And finally, the softmax part to normalize the weights, because weights always mean something like probabilities or the weight given, so it needs to be normalized. So keeping that in mind, we have done this step, and step 4 will be to multiply with value as well. So you'll get your final answer, which is what will be propagated to the next layer. So that's how this Z1 is calculated with the self-attention. And this is just a matrix representation of the above. Above one was a vector representation. This is just a matrix representation and a calculation formula. So that's the basics of this attention formula. And if you want to look at it in block diagram also, that is also there. Now to implement this in code, if you see over here, we need one matrix multiplication between the query and the key. And then we have this scaling, masking. Scaling is nothing but this multiplying with this 1 by square root of dk. Masking is optional. So in encoder module attention, we don't do any masking. Whereas in decoder attention, we do this masking of the future tokens. so that we can see only the past. Because the intuition for decoder model is that it has to continue generating the text which we have already given. So because of that, it cannot see the future because it has to continue that. So that's the reason it gives you mask out the future tokens in that. In encoder, we don't do anything. In encoder, we allow the token to see everything because to learn the connections between all the words. That's why we don't do anything for that. And then we have this softmax. So that is this softmax function. Finally, multiplying with the value. So that is what is this diagram representing, this formula. And in code format, you have this key, query, and value. So when you do matrix multiplication of key and query, so similar to the previous thing I showed, you have to transpose that to maintain the dimensions. And this division by square root is a normalization part or scaling part. So this is to ensure because initially when you initialize your weights will be normally uniformly initialized. But as we start training, in some instance, because of how it learns or something, the weights can be skewed towards one side or other. Like it can be too negative or too higher value. And when that happens, when you pass it to the softmax, the disparity between the numbers can increase more than what is desired. To avoid all such confusion or all such nuances of the calculations, we try to always normalize everything. So that's why we have this for multi-head. So when you're multi-head, it'll impact when your head is more than one. So, and then use that to calculate the scores. And this masking is in case we are using the decoder, but if it's not using, then this is not relevant. Finally, we pass the softmax layer and then drop out also. If it is, we mention it to use, we can use, otherwise it's not required. So your final answer will be your attention score, what we calculated along with the value. So that will be your final output of the attention layer. So here we're actually like giving as output both the final value as well as just the raw attention score. The reason is we'll like see it will be useful in the if you want to visualize or you want to check how it's going, we can use the raw attention score. So till now I was talking about the single head, but mentioning about this DK which refers to the multi-headed. So that multi-head is nothing but if you look at this image, this is the image which we saw previously, but that time it was in orange color, right? Like over here. So this first image, we are focused. If you look at this above bar, this bar consists of eight colors. So 8 colors refers to the 8 heads which we are trying to focus in this image. So if you look at this orange head, where it is focusing on the animal. Whereas if you come down and look at this other head, so for example, this green one. So the green one is focusing it on tired. So the tired is actually one word where it's tokenized as tire and D underscore. So if you the reason can be this it in one head has captured that it refers to the animal, whereas the other head has captured that it has also referring to tired, which also is intuitively making sense because that same animal is feeling tired in the sentence. So that's why having multiple heads allows us to capture multiple such relationships instead of relying on only a single relationship. So that's why multi-head is relevant and important. So if you look at this further image, you can see how these different colors indicate the weights given to the word from it to other words for different heads. So each color represents a head. And you can see how this orange and green, which I was discussing previously, is focusing on these words for it. And the other colors are giving different weights to different tokens. So what exactly they're capturing, that might be abstract, but the intention is having multiple heads can capture multiple relationships which are relevant in the sentence or sequence we are passing. So that is the reason multiple heads are preferred rather than a single head. And how we just visualize that is just by this line. So coming back to the code part of it, we can see that for defining multi-head, we'll have this clone of linear layers. So a linear layer is because we need to pass the value, calculate the key query and value and do the dot product of that. And along with that, we have this dropout again, which is optional, and also this additional DK part. So this is for the number of heads which we will define for multi-head, and that division by underscore DK what we do. That calculation is also saved here. And when we do the forward function, to calculate the key query and value, we pass our X into this linear layers. And the reason we are passing it into this, like because we have multiple layers, we just zip it as one. So this is just a coding nuance. You can also use a separate for loop. Instead of is this thing is actually called a list comprehension, where within a single line you can include the for loop as well as get the values of these three. But it can be split into two steps, where first you write a for loop. It is for every layer in this linear clones what we have done. You have to pass your x into it and save its value into this query key and value. So that is this calculation. After
Yeah.
that, you yeah.
The question might remain same, that why just three dimensions? Why not four or five? And why not variable number of parameters for the query key and value? Why just three?
Yeah, because three is sufficient to convey the information, right? Like, so when you have your question, when you have your potential answer, and when you do that, you get the weight. And when you have what information is actually passed. So if you have additional, what would you want to capture using that?
Hmm.
So they've seen like with this three, it makes some intuitive sense of the reason for having. And if you have less than that, then you cannot capture like, see, with this three, you can have the learnability in the all steps what we followed of the layers what they have designed. We have the learnable aspect, right? But if
Yeah,
you
so the query, if you which is just for this image, right? They
Mhm.
have their own separate linear layers, right? So I agree,
Yeah.
and so they will have their own separate values, right? Query
Mhm.
key and value. But
Mhm.
how we say that the query and key should be multiplied, and the values are different.
Oh,
The
that is
query.
just a thing. Like, okay, you can tell, okay, this why this linear layer is labeled as value. That's initialization. All three are randomly initialized. That doesn't make
Yeah.
any difference.
So we
Just
could
we
have
just
done
call
like
it.
b dot q divided by and softmax of this
Yeah, you
p
can
dot
do
q,
anything.
right?
That is not the issue. We are just giving names for calling. So, for example, in this same instance, I've given
Hmm.
L1, L2, L3 and called it as key query value, right? You can also call L1, L2, L3 as query key value, or you can change the order and do the multiplication. But your end result, you have to be consistent throughout. That's the only thing. Like, you cannot tell one cell pass it, like the one in one iteration of the function, I mean one forward pass or something, you'll call linear L1 as value, L2 as key and L3 as query. In your second pass, you must not change L1 as query and do. Like, anything you can call, but just keep it consistent throughout the code, like throughout your
Yeah,
training part.
so it means that we can choose any two of them, and then we can treat it like that and then proceed like that, and it
Yeah,
will
that's
not.
what is happening. Yeah,
Yeah,
that's what is happening here also, right? See, we declare the cloning of the linear layers, and we just iterate. Like, if I change the order of this, it doesn't matter. Like, query key
yeah,
value, yeah, that ABC or BCA, anything you can call, that doesn't matter.
yeah. Thanks.
I have one question on multi-head attention part. So
Yeah.
there we told that because of this, we capture different kind of information, right?
Mhm.
So this information capturing, does it depend only on the random initialization? Suppose that if in one head, whatever we
Mhm.
initialize, we copy
Mhm.
the exact same weight on the all head, will this different head capture the different information, or it will capture the same information?
Yeah, ideally, because the way we define that linear layer, we define that head over here, right? Where is that linear layer? Yeah, this D model cross D model over here, when we define, it'll be different across that dimension. And the where it learns this connections is when you train it. Initially, such colors and such things will make it'll be uniform across everything. Like, everything will be given equal weightage. But as we start training it, that's when it starts learning what weights are like how the connections actually matter. This head is nothing but an additional dimension, where you can imagine that dimension, like for example, for embedding we had that 16 or 32 or whatever. The dimension will help capture that nuance of different connections. That is obtained only by training. So initially it will be different,
Yeah.
initially, like, because only the dimension part is initialized. We don't
Yeah, so
need to keep re-initializing
so
every time.
yeah, my question was that on the, like, we are not doing specifically anything for other heads, right? Heads are all the heads are learning in the same way as other heads are learning in parallel. So
Yeah,
only
everything
only
is
the only the random initialization is there, which is bringing different kind of, which from what we say that okay, it has learned different features. So if we have the exact same initialization of all the head, will all the head learn the exact same thing? That's my
okay.
question.
That is the thing. Okay, in that case, it depends on what information is back propagated. So if everything is same, then your key query value will be same across all dimensions. Then yeah, potentially you will be learning the same thing. But the thing is, when you have multiple head, the random initialization is key, is helping you introduce the variability. And also when you do the training with back propagation, what loss is propagated along the dimensions will vary. So even if your initialization is uniform, if your weights which is back propagated is different, then still you'll end up with different attention scores for, I mean, different ways of each head. So it because your learning part will be dependent, like what ways are back propagated, that's what will influence the learning aspect of your thing.
But
So
if
even
weights
if
are
your initial,
same,
yeah, even if your initialization is same, that is like your hidden dimension, everything is say 0.1, 0.1, 0.1. But your weight updates what you calculate. For one dimension, it might be 0.2, for one, it might be 0.01. So that change of weight updates can also help in changing the what the head learns, right? So it's not only because of the random, like it might be slower. Like if you maybe do it randomly, it might converge faster or something. But yeah, variability doesn't come only from the initial. It'll also come from the learning aspect, because when you're learning the weights, you'll also be influenced by the other layers, right? Like multiple layers which we have in this model.
okay,
So it's not restricted only to that.
okay, yeah, thank you.
Yeah, so that is the first step where you calculate the key, query, and value. And the second step is calculating the attention. So attention function we already defined previously. And the third step will be concatenating that and applying the final like transpose. So that is just this step. Because why we need to concatenate is because we have multiple heads. So we need to join it together. And then the final linear layer what we have, that is the self-lot linear. So this is the implementation of multi-head attention, which again in diagrammatical format is similar to the self-head attention. It's a similar same image as the previous one, just for recalling how it looks. So now what we have covered is this self-attention part over here by that function, and we also have covered this multi-head attention. What is left is to go back to this positional encoding part. So, and also this layer normalization and this residual part. So for position, as I was saying previously, if you look at this attention calculation, even this formula over here, when you do this dot product, you're not considering any information regarding to the position of the text, right? So your input text, whatever you have, when we do this linear layer and calculate this dot product, we don't have any notion of position as explicitly, like everything gets aggregated in this final value of z. So to introduce or ensure that the position information is maintained, we have this positional layer. So that is similar to an embedding layer. Over here, we have defined it explicitly as a linear layer with the dimensions of this model dimension and also this feed forward dimension. So that's the output what we want. And we have this again back DFFN1. So this is just like a two-layer linear layers and with a dropout layer where if you pass X into the input, what we get is your input X. So this is same as this function over here. So you have your X, you pass it through one linear layer, which is called self.w_1, which will do X into W1 plus BW1, that's a bias term. And the whole thing, this max of 0, W1 is the ReLU function. That is a normalization. And then dropout is again optional, or if you want to have it, you can have it. And then we have this another linear layer with W2 and B2. So this is the definition for the feed forward linear layer what we have, which contains positional information also, like position wise feed forward linear. So another thing is that, yeah, this part if you have, it will do the calculation of this step, this blue color box over here. Once that is done, we'll have our final step left out is this residual connection. So this also we defined earlier using that module function, right? That the sample submodule. So that as in diagrammatic way, what we're trying to do is trying to have X directly added to the output of whatever we did over here, this weighted layer, ReLU and weighted layer. So for that, the reason for having such things is all these advantages which are listed over here. And this is done by like previously other research papers would have found out some techniques. All those techniques come together in this paper. So that's how why dropout is required, why residual is required, why we need like instead of one head, multiple head, all that things. Different like research papers earlier would have found out some small things saying that layer normalization is useful for training, or residual connection is useful, dropout is useful. So those ideas were aggregated in this paper coming together. And all of them, when switched on, like when all that points were kept in consideration, the performance has been seen better than when we didn't consider all of that things. And this layer norm definition is nothing but the normalization. For normalization, if you see what we have is one parameter layer of ones and one is of zeros. And what we are trying to do is just normalizing the x input. So we take the mean of x, we take the standard deviation of x, and we do this calculation of x minus mean divided by standard deviation. The reason for this epsilon is to ensure if standard deviation is very, very low or close to zero, like it doesn't cause division by zero error. So we have this self dot epsilon. And this whole thing we have self dot A2, that is this parameter of which is nothing but initialized with torch dot ones, input is ones. And the self dot B2, which is this zeros, like weights and bias. So this is like an explicit mentioning of linear layer. We can call one linear layer and pass this part as it. But this is not, we don't want the whole linear layer, like to explicitly mention, we can also call it like this. In a parameter, that's one layer. What we are achieving from this is the normalized version of what text we pass into it. So till now, what we have covered, if you look back at this image, we have seen this input embedding. I mean, we assume it's embedded, and then we take the attention function and we do the normalization and addition with the skip connection. Then we do this feed forward, which is mentioned over here, position wise feed forward, which definition is two linear layers as per the function. I mean, definition of the function. And that is also added and normalized. So since we have covered this part, that means we have covered the encoder block completely. Only part left now is the decoder part. And if you see the decoder,
One question I have in layer norm.
Yeah.
So this is different from batch norm, right? So if you go to
Yeah.
your function,
Mm.
if you instead of -1, if it make it 0, will it become batch norm? So if you can just explain the difference.
Okay, this part you're saying.
Yeah.
Yeah, so we want to take this normalization across this layer wise, not the batches. Yeah, correct. So because your X shape will be, if with the multi-head, it will be T cross T. In that T dimension, the last one, we need to take this mean and keep the shape. Keep dims is nothing but the 3-dimension will be maintained. If you keep it as 0, that is the initial one, then yes, it will become the batch-wise normalization, which we don't want now.
So B and T will be here, and E will be across E. We are taking the mean.
Yeah, E across E, but the thing is, we're calculating this layer norm after we do this attention, right? Where is that image? 1 minute. Yeah, we are calculating this one for this Z. So Z's dimension is B cross T cross T only. I mean, or not T, I mean, depends on what head, yeah, T, depending on that. So E will no longer be there.
I mean, head will
Because,
not be there. Yeah.
Yeah, head will also not be there, E also will not be there, because your value dimension is having T cross H, that head one.
Yeah, thank you.
Yeah, so the decoder part, two parts of it is very identical to the encoder. Only the difference is in one having self-attention block, and the second one, your input to your self-attention in decoder is actually called cross-attention, because we are getting the query from the outside, like or the key and value from the encoder and getting the query only from the decoder. So that we'll just see now in the code part. So for decoder, just looking at from top-down approach, we have this initial layer with the clones, again, similar logic to whatever we did for encoder. And we pass the text into this. And here also we have this memory part. So this memory will be defining more in detail when we go to the exact decoder layer function. And this is actually an image of unidirectional self-attention. So this image might look little intimidating or confusing, but what we are trying to say is that your given token will actually be able to see only your past tokens. It cannot see your future token. So that's why if you look at y0, if you consider y0 to be the third token, then you can see the previous two tokens, but you cannot see the next token. Similarly, for y1, you can see only the past and the current token. You cannot see the future token, which will be y0. I mean, the numbers can be in reverse order. But what we are trying to say is that you cannot see your future currently. You can only see the past and current step. So for that, what we do is we take information from the encoder. So this y is which is the output, and we also calculate the query and the values and keys. So in one's that two steps of attention. In one's first block of attention, which is self attention, we calculate the key query value all from the output, expected output of the decoder or the whole for the input. And the second part where we have this influence of encoder with that we call as cross attention, we'll calculate with query from the decoder and key and value from the encoder part. So that's how 2 times attention happens in decoder, whereas in encoder only one self attention is happening. And the self attention is happening in decoder is having the masking of future tokens. So that's the difference. So otherwise, architecture wise, similar layers, additional normalized feed now.
Can you just explain it again? The cross attention part.
Yeah. So
To
the
decode a part of
yeah,
attention that is happening 2 times, right?
yeah, 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 yeah. So first step will be your self attention, where difference between the encoder and decoder is that in encoder you'll attend to all the tokens. In decoder you can attend only to your current and past tokens. So that's a difference in self attention for encoder and decoder. Then in decoder we have an additional layer of cross attention, where your value and key will be coming from your encoder and your query will be coming from your decoder. So if you see the calculation of key, query, and value, we pass that x into linear layers, right? So that x into linear layer, what we get for key and value is coming from us from your encoder side. So that's the arrow mark over here. But your query part will be calculating from this decoder's input. So your input to your query layer will be taken as this y. So if you consider this input of encoder as x and input of decoder as y, for query calculation in decoder for cross attention will be from y, and the key and value calculation for decoder in cross attention will be from x, which will be nothing but the output x in the sense that output of the encoder, not exactly the input x. Like, yeah, if I'll go through that code part also, so it might be more clearer. So coming, this is just the definition of the function.
So
We'll
how the
discuss that.
two attentions are basically, added or used. We have the cross attention, the self attention, both.
Yeah, I'll go through that. We have this separate section also for cross attention. I'll just go through that in detail. Yeah, this is one image of self attention part. I think, yeah, this part is. This is the cross attention part. So if you look over here, you can see this. We have this values and keys which are coming from x, and your query is coming from y. So your x is actually what we get as output from the encoder layer, whereas your y is actually the input to your decoder layer. So when you calculate the cross attention, our intention is whatever output I have currently, that will be the what I'm looking for, or that will be the question. And I'll try to match that to my input X to see what input is relevant to my current question. So in other words, you imagine the input to your text is one sentence in English, and your expected output is one sentence in French. So now, for example, you have a token that French is Y and your English is X. Okay. So now in your Y, you have one token which you have calculated your query for. So what the intention of this query in Y is, you want to find out which words in the X or which words in English mean this word in Y or this word in French. So you have your French word and your English words. What your intention is, which English words mean this French word. So if you have a high score for this, that means this French word potentially means this English word. And if you have a lower score, that means this French word doesn't mean this English word. I mean, in case of translation, for example. So how we can capture that through this cross attention is that we take the query part from the French, like the output, that's why, and we try to do the dot product of that with the key from the English side. So what we're doing is we have your English information as key in one side, and you have the query information from French in other side. When you do the dot product, potentially whichever has a higher value will indicate that maybe that translation is more, that word is closer to that word. That's why it will be given more importance. Second thing is that we also have our value from the X part. So value can be also referred to as what information is actually conveyed, right? So since in the end we want to predict our output and we want to take the input into consideration, so our desired part is output, right? So for our given input, along with this information of weight, what I've calculated, what will be the expected output. So that's what we're trying to capture through this image also over here. So you take your value from your X side, you do the softmax of your key and query, which is taken from X and Y, and you do that. I mean, you add addition and normalization because that skip connection is added back to your Y. What we finally get is trying to predict the next potential token. So that's like we're trying to integrate information from our input and using that information to better predict our output instead of directly relying. I mean, that's how we can connect the input and output together. So that's what we are trying to do through the cross attention. So if you look at self attention, if you focus on this color over here in the white image, that's self attention. Your key, query, value all are coming from the same part. So this will be the first step of your decoder attention, and then you do layer normalization and addition and all. And second time when you do cross attention, where your one side, your values and keys come from the X side, and your queries come from the Y side, and then you do the same formula and do addition and normalization. Then you will get your output of the second time. And now you do this feed forward and normalization with your final softmax layer, that is a generate function which we declared in the beginning. Then we'll get our desired output expected token. So that's the reason for, I mean, intuition of cross attention, which in code base, we can see that initially we declare the self attention and then the source attention and then the feed forward and also the sub layer, that's for the skip connections. And if you see the step by step, this M is like memory. So this is actually what we're trying to capture, this output of encoder to the decoder. So that will be given as input over here. If you look at when we call this function, you'll see what exact value the memory will take. Like below, we'll be seeing that. So if you see the self.sublayer, so this is to ensure that skip connection is maintained. First, we do the
memory is the output of the encoder.
That we need to use for cross attention.
That's the same as query and key, right? Output of the
yes
encoder.
Yes. So from memory we'll be passing that over here when we calculate self attention. Yeah, that will be value and key, not query and key, but value and key.
Yeah, value and key.
Yeah, correct. So that's why in the first layer we'll pass all inputs. I mean, for key, query, value calculation we'll pass X, but for the second cross attention we'll pass X as query, and the key and value part will pass the output of encoder. So that's the memory part. So that we are calling it memory, that's just a variable name. You can call it anything you want, like maybe some output of encoder or whatever. And then we also, because this is coming from the encoder, we have that source mask. The original one is the target, so we have the target mask. And the sublayer part will ensure we do this skip connection. So if you look back at this image over here, we also have the skip connections, right? This dotted lines. So to ensure the dotted lines, which we defined as this sublayer previously, so we are calling back that function, that class. So this part will take care of the two steps. Now finally we do the feed forward, then we'll have the final decode block also defined. Now for this, the key part over here for this first self attention is the masking, which I was talking about before. So how we want to mask is, we want to mask in, like, for example, you can imagine this matrix where in your first time step, you can see only token 1. Your second time step, you can see the first 2 tokens, and third time step, you can see all 3 tokens. So that's what, like, in this function output, if you just call this function, run this function, like currently it's not connected, so I'll just show this output, but you can try it out in your this thing. So this function, what it does is, it takes your size, expected size as input, and it calculates this u. So what is like called triangular upper matrix of torch.1. So what happens is, your torch.1's of attention shape output will be identity ones matrix. It will have a matrix of shape, attention shape. So for example, if it's 3, you'll have a 3 by 3 matrix with all ones. And then when you call this torch dot, this TRIU is nothing but triangular upper. It'll give you a upper triangular matrix where your diagonals will be, and diagonal also will be 1. So the upper part will be 1. That if you do this equal to 0, so wherever it is 1, it will be given as false, and wherever 0 will be given as true. So actually you'll get a lower triangular matrix. So this one way of initializing a lower triangular matrix. Otherwise, another simple way is instead of you put L over here. Then we don't need to do this additional step of this masking. Automatically, you will get this part. So since it was mentioned as upper triangular, you need to do this mask. Otherwise, if you use the lower triangular matrix, because that's what we want, we can directly get something like this. So to see how, just visualize how it looks. So this function is just for plotting the graph. So it's not much relevant, but just in case you want to see. This is how the lower triangle matrix. So wherever it's yellow, it's considered 1, and wherever it's purple, that's 0. So intention is you can see only your current and past tokens. You cannot see your future tokens because that's what we want to predict, right? If you already see the future and you're predicting, then there is no point. You can just copy that back over here. You don't need to learn anything. So to avoid such shortcuts, we have to hide that part. And coming back to the image, yeah, we have completed this connection of attention. So that's how this attention differs from this attention. And here we call it as encoder decoder attention, or also called as cross attention. And then this layer, and this you multiple times decoder modules you can have, and then your final output will be passed to the linear layer and softmax, which we called as generate in the beginning. Now the only thing which can be left is the input text, which will be text. We cannot we have to convert it to the embedding and pass it, right? So for embedding, we actually initialize the embedding layer over here. So this nn.emily will depend on the vocab size and this D model. So previously you would have seen something D model is propagating throughout all the modules functions. So what the D model is nothing but the dimension what we are mentioning. So embedding dimension we call it as. So depending on if you look at this BERT or GPT or all the things, different models have different embedding dimensions depending on their tokenizers. Since in this notebook we are trying to do everything from scratch, you can define your own dimension what you're interested in and try to use that to create the shape of the model. And your forward function will be nothing but you pass your call your embedding layer. So that is this embedding layer is called LUT over here. So just pass the embedding layer. And then we also have this position encoding, right? So this positional encoding is different from that feed forward position. So both things are not same. This is for capturing the what I was telling that time that code it was not covered, but this is the code part of that. So where your aggregation average will not take into consideration the position difference. So that's why in embedding itself, you're trying to incorporate that information by having this sinusoidal function like mac dot square root of this thing. So normally, if you look at these other models, they try to use some sine or cosine function. Because of the periodicity of the function, it seems to be helpful in determining it capturing the positional differences. So that's a approach which was used in the paper also. Otherwise, like normally, if you look at this pre-trained models, we don't need to explicitly specify the positional embeddings because it will already be taken care of when you call their embedding module. I mean, their tokenizer you call, everything will be taken care of. Since this was from scratch, that's why we have this additional embedding layer. And if you look at in detail of positional embedding, this is like just the intuition. Like you would have seen this image in word to vector format where you'll have your different words which is converted to vectors, and you do the addition, or you want to find nearby words, you can try to use that words together. So in this context, what this image is trying to tell is that you have your queen vector and king vector, but you want to say that the word queen and should come next to king. So to capture that position, we try to add this white vector of considering of positions in such a way that order is maintained, some order flow of information is maintained. So again, this textual information, that's what sine and cosine functions they try to use, which is defined in this function over here. So this part you can see like we try to define a dropout layer, which is again optional. We start with the zeros layer. So zeros layer dimension is maximum length and D model. So whatever D model the embedding dimension. We also have this position. A arrange is nothing but it will create a vector starting from 0 to max length, and it'll try to create, like for example, if max length is 10, it will create an array of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a proxy for using a for loop to create an array or creating a range of numbers. And unsqueeze means it will create an additional dimension along the first index. So here what we try to do is we take this array of 0 to D model, and comma 2 means we will be having this range with every step size of 2. So if you don't mention anything, like by default set size will be 1. But because you mentioned 2 over here, it's like we want all even numbers. And we're multiplying this minus math.log by 10,000 and dividing by the embedding dimension what we have. So if you see, this is exactly the formula which you have written over here. Sorry. That's the formula. And we see to calculate that we pass that information into the sine and cos of the torch dot sine and torch dot cos. So we calculate the sine and cos of that and start saving that. So since we pass an array of numbers, we'll get also an array of numbers. And its output, again, they're trying to unsqueeze along the 0 dimension, means adding like a batch dimension. So this is just this registered buffer part you can actually ignore. This for memory optimization to save the part. Otherwise, it's not relevant to the code function of that. Functionality of the thing doesn't matter from that. And when you call forward, what is happening is you take your input x, you pass it through this self.p. So what do you have over here? This torch.zeros. In that you take this layer. In this layer, when you call this layer, it will calculate this over here, this torch.sine and cos for x that is taken as input. And this required grad is false is we don't want to explicitly learn the position embeddings because that is basic input to the model along with x. So we are treating it as static information. Since our x is not changing, we don't want information about the position of x also to keep on changing as we learn it. We want to learn concepts or relationships between x, but not just the position of x. So for that, we don't need to update its parameters. So we're keeping required grad equal to false and dropout layers also maintained. So this is for this function, two functions like this line and code, these 2 lines in code format to ensure we capture the positional information of whatever x we pass into that. And if you want to look at how that line looks, so since it's a sine and cosine wave, you can see by changing the dimensions what we're mentioning over here of this D model and of that max length. And we can see what we called it with forward is for 1 cross 100 cross 20. So torch.0 120 in the sense we are having our max length as 100 and D model as 20. So your input length, token length can be 100 maybe, and your dimension is 20. In that case, if you try to visualize that image, you can see this colored lines of here of different dimensions. So for dimension 4, you'll have this type of curve. And for dimension 7, the green one, you'll have this type of smoother curve. So depending on which dimension or how we choose, that's how this repetition, the sine and cosine wave order will change. So this is just to capture some notion of position instead of keeping it, instead of losing it out completely. That's just for capturing the position part.
I have
And
few
this is
questions on. So the number 10,000, was there any reason to select, and does it depend on
no,
the token length?
10,000 is for depending on this function. Yeah, you can see this for information like this textual part I didn't cover, but yeah, it's a formula which is given in the paper. More details can be seen over there, like that intuition, that there's a formula part. So we can maybe change you this max length over here. So that part and all we can change. But this formula, this 10,000 is kept in the formula.
So it doesn't depend on the token length. If you have longer
No.
token, do we need to increase? No.
See,
Okay.
because actually, if you look at this line, the wavelength, because sine and cosine waves, what we're having, it starts from 2 pi. That actually pi is coming as PA over here, but from 2 pi to 10,000. So that's the range of the sine and cosine, the sinusoidal curve. So because of that, the formula has 10,000. That has nothing to do with what embedding size we choose or anything.
Okay, so I was thinking if it repeats. Okay, I will see. I have another question on this, the timing, this masking what we did, and that created a triangular matrix, right? Now you have like 4 or 5 dimension is getting increased. Like how are we passing this? Is it like, are we predicting one word at a time, or all the time step we pass at once to the model?
This actually, if you look at the final calculation, everything is in matrix multiplication. So at one time, what will happen is in your inputs, if you have a batch of inputs, your first element of the batch will be having 1 token, your second element of the batch will be having 2 tokens, and so on until the end. based on how many ever batch size you have. So when you predict your first, for your information for your first token will be only one, whereas for your information for your second line will be having two tokens. So that's how in the output what you get, your first line will be having information, I mean the out prediction based on only one token, whereas your second line will have prediction based on the past two tokens. Then third line will have prediction based on past three tokens, and so on. So that's how like you can look at the past and predict the future, and you can do this in a single one shot manner. You do not have to wait until the first prediction is done to use that as input for the second one. So that's where you can overcome the limitation of RNN over here, since we are
So it
having
means
this kind of, yeah.
batch size and token size should be same in that case, right? Because if you are having for one batch one token, second batch two token, then there is a
I mean,
constraint
you will
always
have
batch.
padding tokens as well, right? You'll always have padding tokens, so that's fine.
Oh,
See,
so
see
if there is
normally,
X,
hmm,
go ahead, go ahead.
yeah. Now what I'm saying is normally any input we have, when it actually does the calculation, normally we don't divide X as one token, two token, three token. What we pass as input is just X and Y. So X, suppose X length is 10 and Y length is suppose 4. That means we
Mhm.
want to predict 4 tokens looking at this 10 tokens. When you're doing that, when we're predicting the first token of the 4 output Y first token, we look at the 10 tokens of this input and we'll predict. When you look at the second token, we look at the input X and we'll look at the first token of Y and predict. When you want to predict the third token of Y, we look at the first two tokens of Y and the whole X and predict. So that's how we'll get the 4 tokens of Y. And the way we do that 1, 2, 3, 4 is using this by multiplying that attention thing with the mask part. So because when you pass Y, we pass the entire 4 dimension directly at once to Y. We don't break Y into 1, 2, 3, 4 and pass. How we you do that through the code part by having this matrix of ones, I mean with diagonal way, so that when you multiply this identity matrix into X, what you get is actually something like that. So if I go back to this part, I don't know why it's not it was not running that time, but I'll just see if I can show. Okay, I'll go back here.
So input should be replicated that many time, right? So if token
Yeah,
is 10,
it'll be taken care of automatically. So if you see this A, I'll just show
okay.
this part. Yes, suppose imagine A is something like this. So this will be the for the encoder part. But when you look at the decoder attention, and I still in the triangular upper or triangular lower matrix, so you'll get something like this where you'll have ones. And when you do this with X, right? Yeah, automatically I mean, this might be big to see, but it'll automatically capture the reference numbers. Like if you look at maybe 0 part of that, just
Okay, okay, I understood.
yeah, you can try to, it'll start adding in a cumulative manner. It won't add everything at once. So
Got it.
that can be take. That's why we don't want to explicitly write any for loop for that. So we're using this attention matrix to,
Okay.
I'm not attention, maybe masking matrix you can call, because we are already calling attention something else. This masking matrix. So if you look back at that masking, I mean attention function we defined earlier, we had one parameter of mask, right? So over there, if you see that function of attention which we defined over there, we have an option of mask. What mask we'll be passing is this mask. That's how we'll be able to calculate the stepwise one and hide the future from that.
Got it.
So that, yeah, this last one is this generator. So this is the same thing which we defined earlier in the beginning also, having one linear layer and one softmax layer to get the final output. And this final make model is calling the all the modules which we separately, all the classes we define separately. We are trying to aggregate it together to call to make it a single model where we call this encoder decoder. So the very first class which we defined the encoder decoder. And that we have encoder block and we have a decoder block, followed by the sequential layers for position element. So all is input to the encoder decoder blocks. If you go back to the encoder decoder block in the beginning of the notebook, all these will be taken as input. In the initialization function, all these will be initialized in the generated part. So because we have defined all the copying multiple times, everything inside the functions of the copy module and clone module, we need not explicitly do anything for that. We can, now that we have defined the model, we can look at the model parameters or print it out and return the model. And for the currently what we have done is we have defined the model and we are able to get some like info, like we can pass input to it and get some output from it. So that's what this inference test will be. Like you can take any x and pass of some size, and you can take some source tensor, and you can have some source masking, just one of one. That means don't need to mask anything. Wherever mask is one, that means you're going to look at that. And you also have this memory to be the output of encoders, which we calculate. And for target, we're having this dot zeros. And then this is just for a dummy. You can actually change it depending on what you want to try it out and try running it. So what we have, this part of the code will do is it'll define your function, and it'll be allow you to pass input and get output from your function. But what you're actually interested in is to actually train the function, right? So that's what something you can explore on. And this resource over here, which I have linked in this below, that will explain the concepts again. Like he will actually go through the GPT model, which is called a decoder only model. So actually, I don't know if how much time is left, but the next notebook of BERT is an encoder's model. So that will show you how this attentions will be relevant in encoding aspect, whereas GPT is a decoder based model. So the encoder part is not considered in that case. So more details on that, like in this resources, you can check out. Yeah, and that's the part for transformers. Any doubts you can ask, or you can go through it later, I mean, on your time, and get back later also. So that's about the transformer part. Now maybe I don't know how much time is left, but another notebook is also there. Only 10 minutes is left, I think.
Yeah. Yeah. So like, sir, are you there? Hello, sir. So the class is from 8 till 11, right?
Yes.
Okay.
So is the current notebook which is being shared on the presentation, has this been shared? Because I'm not finding the same in
Okay. Like
here.
from our information, like sir has already shared it in the chat, I think. Could you just check that?
But that doesn't have many of the, the vector the matrix multiplication things that we got to
Okay.
see in the that part, right? That is quite
Okay.
a refined version of what we saw in
Uh,
the.
yeah, that is. However, it's there in the video. So if you go to the video from Andres Carpetti, you can walk through there itself.
Yeah,
Yeah,
but
that's
it's like
right. That's actually, yeah, you mean that, I mean, I'll just share and ask it again.
the exact notebook that you were showing in the current,
Yeah, the exact
session.
notebook I was showing, I shifted in between to just zoom into that multiplication part. I showed this is the main notebook which I was explaining. Only this part, this is just a copy of that with this additional lines where line by line I just try to print out the things. You mean this part, right?
Yeah, yeah.
Yeah, that's what this exactly is actually covered in the video link which I had shared earlier. Like it's just in this link. So that's why I
Yeah,
didn't think.
I will go through the video as well, but can you just share this
Yeah,
notebook
yeah,
as
that's fine. Yeah, that's fine. Yeah, I can add this part as well. Yeah.
Hello, sir.
Hello, I guess the first notebook is done, right, Aishwarya?
Yes,
Yes,
sir.
sir.
Okay, okay. And the second one will take time, right?
Yes, sir.
So in that case, I think we can conclude here today and maybe take this
Sir, your voice is not audible, sir.
You are mute. If you are speaking.
Yeah, got temporarily disconnected. Yeah. Okay. So, yeah. So the second one will take how much time, Aishwarya? I think around 1 hour, right? Minimum.
Yes, like yeah, 1 hour.
So then, right. So then, let us conclude today's class here, and we'll take it up at some later point of time. I hope the discussion was useful, and whatever you got in today's class could be helpful at some point of time. Okay. Thank you, Aishwarya. Thank you, Maharaj.
Thank you, sir.
Thank you, sir.
We end the session here today.
Sir,
Thank you, sir.
sir, it was great. Can we have the link of the BERT notebook as well?
We will share that. No, so whatever has been covered, that link will be providing. And
Oh.
regarding the other, we'll also go through what is there and if any modification needs to be done.
Sure, sure. Thank you, sir.
Thank you.
Thank you, sir.